This topic is about concurrency control. There are many problems when we have transactions executed at the same time. The first one is the loss update. Is when transactions try to modify the same data, and one transaction reads the data, and then another transaction reads the same value. And the first transaction changed the data, and now the information, the second transaction also tries to modify the data, and the last transaction that changes the data is the one that has the value. The other case in which we have a problem with concurrency is when a transaction reads data that was modified by another transaction, and then the first transaction aborts. That's a problem that is called the dirty read. An inconsistency analysis is when we have several transactions executed in parallel and they are just reading data. We're going to see an example of each case. The loss update. So we can see that we have two transactions here. Transaction 2 starts to execute and it reads the value of X, which is 100. Okay, and then on time 2, the transaction 1 starts. Next, transaction 3 is gonna read the value of X, which is 100, and later the transaction 2 changes the value of X. So internally here, the value is going to be 200. And transaction 4 changes the value of X. It read 100 minus 10 is going to be 90. But then this transaction is going to change the value. This transaction already read 100 plus 100 is going to write 200 to the database. But the first transaction, it has the value of 90. So it's going to come and write 90. Then the transaction commits. And when it commits, it completes, and then the second transaction changes. So when we have two transactions like this, one is subtracting 10 and the other is adding 100, the transaction that we lost was the transaction that wrote the data first, because when this transaction came, read 100 and changed it to 90. So the addition of $100 to our account was lost. This is an example of the lost update. Dirty read. We have here two transactions. Transaction 4, which is going to add 100 to my account, and then transaction 3, which is going to subtract 10. In this case, we move the transaction 3 to read the data after the transaction 4 wrote the data to storage. Okay, so here the transaction reads 100 and adds 100, so the value is 200. Writes 200 to the database. And then this transaction reads 200 and it changes to 190 because it's subtracting 10. And at the same time, this transaction roll back. So rollback means that the 100 was never deposited in my account. However, this transaction already read the value with the 100. So at the last minute, I'm going to have the value 190 because that's the value that this transaction wrote. However, the transaction 4 was canceled. It was rolled back. So the $100 were never into the account. So the correct value should be 90, not 190. So this is the problem of the dirty read when transaction 3 read a value that is no longer valid because the transaction did a rollback. The second example, or the third example, the inconsistency analysis, is transaction 5 has multiple values. Okay, transaction 6 modifies some values in the execution of T5. So this transaction 5, is reading X, changing, subtracting 10, and adding 10 to Z. So transaction 2 is just reading the value of X, Y, and Z. So the value of X, Y, and Z should be 175. And it doesn't matter if we move data from one variable to another variable. At the end, since we are adding the three values, it should be 175. However, the value is 185. Why is that? Because when we start executing, I read the value of x before was changed, and I read the value of z after it was changed. So I did not consider the $10 that were subtracted from the value of x. So that's why I have a value of 185. How can we make sure that these transactions do not operate like that, causing problems? There are two concurrency control mechanisms. One is logs and one is timestamp. I cannot see which one is the best mechanism because all of them have advantages and disadvantages. The use of logs. Logs, I need a log for every time that I read a value, and that will be a read log. And when I modify a value, I need to acquire a read-write log. The problem when I use logs is that I can have a deadlock. A deadlock is when processes are waiting for events that never occur. That means that the log will never be released. The other technique is called timestamps. Timestamps, I write the timestamp every time I read or I change a value on my data. If I detect that the value that I read was changed by another transaction, the transaction has to be aborted or rolled back. So the problem with the timestamp technique is it is an optimistic technique, but because I can't always have values that are not valid anymore, I may have to do many rollbacks. So the main disadvantage on the timestamp is the rollback, and the main disadvantage with the logs is the deadlock. The most common technique is logs. So the algorithm that is using to log is two-phase logging. And I have in this algorithm two phases. One phase is when I acquire logs. The transaction can only request logs, and log needs to be acquired for each element to be read or modified. And I have two types of logs: the shared logs that are for data that I'm gonna read, and several transactions can get the log. And the exclusive logs, which are for writing, only one transaction at a time. And if the log is busy, the transaction is logged on the waiting list and automatically is activated when the resource log is released. If the log is busy, the transaction has to be waiting until the other transaction completes the task and releases the log. So in the phase one, I'm just going to ask for logs, acquire logs. I can see that in this example. So this is the phase one. I acquire a log here, and acquire a log here, and acquire a log. It's like acquiring logs is like stepping on this. Okay. The second part or the second phase is when I start releasing logs. Okay. The releases logs. Once you release a log, you cannot ask for a log anymore. Okay. And when you release a log, maybe you can wait a transaction. And with this two-phase locking, I do not guarantee the isolation. Okay, so I have here, I am asking for a lock here, another lock here, another lock here, and I start releasing locks here, another lock here, and another lock here. So this is two-phase locking. I cannot have something like it's going up and down. Okay, and in the shrinking phase, I release the locks. That's the green part. Because the two-phase locking does not guarantee isolation, what I have to do to avoid process entering in the middle of the transaction, I have to move all the release at the end of the transaction or at the commit time. That's the strict two-phase locking when I release all the logs at the end of the transaction. So in summary, locks are released until the transaction commits, and two-phase locking does not guarantee isolation. Two-phase locking does not guarantee isolation because a transaction can enter in this moment, but a strict two-phase locking does guarantee isolation because it releases the locks at the end of the process.